Okay, good evening everyone. My name is Eduardo from Brazil, and I will talk about this paper today. This paper is an intelligent digital microfluidic processor for biomedical detection. So let's start. First, I'll go to the introduction part. The proposed processor. So this processor has this potential architecture, solves lots of traditional development bottlenecks and to implement these points. Easy control, the easy to monitor, system automation, high accuracy for biosafe detection purpose. So we'll talk about during this presentation what about these items. So, and integrates functions of microfluidics attenuation, droplet locations readback, and high sensitivity measure window. All these items is part of the system. So all these parts combined together will make this processor more than the other ones. So that was this paper is about. Okay.
So they just suggest a certain type of the system integrated to its three parts.
Sorry?
So they just suggest the system.
Yeah. It's
consisting of the three parts.
Yeah, it's an intelligent processor. The thing about the human, I just saw on the internet, so I just to add in this presentation. It's one of the possibilities, but actually this is a microfluidic chip to combine these items to make better chip. So okay. So first we need to have look at some important information. Sorry. We need to look at some important information. We have a lot of abbreviations here in this presentation, so I did this subtitle part of EWOD, META, MC, PVT, ITIL, HV, so all these abbreviations is used in this paper. So I just listed here, so if we need something, you just go back and go forward. Okay, one of the important information is the size. This is fabricated in standard 0.535 micrometers. And it works to integrate with 900 microelectrodes. So we have a kind of table I will show you later. And we have these 900 microelectrodes that will be responsible to detect the droplets. So we are talking about microfluidics. So this project wants to detect the microdroplets and to guide the droplets in the system to do the experiments. And the measurement window is 3.2 square millimeters, where the high sensitivity capacitive readout circuits occupies only 0.048 square millimeters. It's very, very small. Measurement results show that microdroplet actuation and 2D location map activate under 1 kilohertz. So detecting by this, you can face it like pixels on a screen, because these microelectrodes will detect the droplet and then will send this information to processor and to use this in a graphical interface. So it's like a pixel. You can face like this. So droplets location. As I said, you have this like pixel, so you can detect where exactly the droplet is. So the droplet location map and the reaction behaviors are visible on a two-dimensional graphical user interface due to the microelectrode dot array. That's the system used to do this 900 microelectrodes. So that is an array that will detect the microdroplet. And this architecture and capacitive sensing technology enhance system automation and is achievable. Operation. Measurement results show that microdroplet attenuation and 2D location map are activated under 1 kHz. In addition, the function of digital signal extraction, processing as well, the statistical analysis can be operated under 1 MHz respectively. Okay, any questions so far? Okay. So let's start to see the bioprocessor architecture, how it works. Here we have a schematic view of the table. This is not from the paper I just found on YouTube, just to illustrate how it works. So here is the schematic view about this paper. And for bioassay operation, microdroplets can be created from the expected reservoir, where actions and droplet volumes can be presetting according to the user definition. So you have some reservoirs here in the plate when you will inject the liquid. So you can decide what's the volume of this microdroplet. You can decide by using the graphical interface. So the 2D graphical control patterns can be fed into corresponding MC, that's microcells, with daisy chain for several microfluidic situation, for digital signal processing of droplet location map. Each MC can sense the capacitance difference. That's why these microelectrodes can detect the droplet, because of the capacitance difference. When there is a droplet there, the capacitance is different from when you don't have the droplet.
So the purpose of this structure is to detect the droplet.
Actually, it detected the droplet is apart, because the main purpose of this kind of system is to, how can I say? For example, the laboratories use big equipment to separate the liquids in a lot of tubes and pipes. So there's a lot of cost, and the machines that separate these liquids and mix and make the tests is very expensive. So they call this a lab on a chip, because you can control the droplets in these electrodes using electrostatic force. So you can mix, you can make hundreds of experiments together. You can put drugs and blood and everything you want. There is in a way of a droplet to make these experiments. So if you have a big plate, you can just maybe 1,000 experiments all together, and you can get the results of this mixing, the time of mixing, the velocity, so you can analyze the mixture and everything else.
Okay.
So this is a schematic view I'll show here. This is the reservoir, because it's not showing here, but here you have the reservoir that will flow the liquid here. So this red one is the liquid being flowing, and this is the droplet separating from this main fluid. Okay, so let me just see here. It's too tiny. Okay, so microdroplet is creating here by this green one. So we have the reservoir, the fluid, and it's separating. You can check that there's blue one and white ones. The blue ones is activated and the white ones is not activated. So this will make the separation and the creation of the microdroplet. Okay? So we have the measurement window here. We have the droplet mixing. It's another example. When you mix two droplets, so one will reach another. So it will mix, and you can analyze this. And the droplet cutting, as I told you. And the droplet moving. So it's just to figure out the movement. So, as the figure 1 says, the illustration of A, microfluidic operations, and B, the proposed block diagram. This diagram, I need to be honest, I didn't understand too much. I studied the background, but it's very complex. What I understand is the parts of the system, and you have, for example, 1, 2, 3, and 39, and 900. So this is the microelectrodes. I don't know why they put this way, not side by side. I don't know exactly what's this, but this is the system schema. Okay. Okay, that's. So let's take a look at this example video. So the droplets are moving by electrostatical force, energy, and he's testing the speed. So can you imagine 100 of this? You can make a lot of experiments. Just increasing, and now preparing to mix. So you can use this to make a lot of tests. Okay, so you can use this to make hundreds of tests together, and you can just use this instead of big lab. You don't need all the chemicals, all the reactors, and all the machines. You just need a bioprocessor. Okay. Well, let's see the bioprocessor first section. This is how it is assembled. So here we have a hydrophobic layer. We have this here too, and here we have silicon oil inside. Here you have the droplet. In this experiment, they use deionized water, and the silicon oil and the droplet. First of all, the silicon oil will avoid that the droplet evaporate, and the system can detect what is silicon oil and what is the droplet by the capacitance difference. So using this, you can know exactly the place where the droplet is. So we have a dielectric layer. It's important to say that they use here I2 glass. Do you know I2 glass? ITO glass? It's an indium oxide. I'm sorry, just a moment. Indium dioxide. That they use this glass because this kind of glass conduct energy. It's a conductor. So they use this, and this hydrophobic layer will avoid that the droplet just grab here. You have all the electrodes here, and the microcells that is attached to these electrodes that will read the capacitance difference and send the information to the processor, to the CMOS. So we have the subtitles here. This is glass here, the ITO glass, Teflon to cover because Teflon is very hydrophobic. Dye water, silicon oil, passivation, metal, and the substrate. Okay. So the routine, how it works. That's why the title of this paper is an intelligent digital microfluid processor, because this kind of system has self-testing. So it will check every time what they need to do and give the response and show the result in the graphical interface. So we have another schematic view here. It's very difficult to understand this. So you have the high voltage here that enables signal in high voltage. So looking this line, you can see the difference when initial droplet's location read back. The droplet moving, so it's characteristic. Current droplet location sensing, and next droplet moving. And here you have the droplet detection, sensing result read back, that will send this result, what it sends to the program. and the microfluidics operation manager, and next droplet actuation pattern. So processing routine for droplet actuation, location sensing, and automation scheme. That's why it's intelligent. Everything is automated. You have automation everywhere. So there is a, how they say, a pseudocode for this bioprocessor. So first, you have the threshold. You just click here. Okay. No, not here, sorry. Here. So you have here the threshold, trimming, and you have the set of tensing that he will check if it's bigger than the threshold, that is bigger than the parasitic and PVT variation. This parasitic is parasitic tension that is in the microelectrodes. So you have a loop here. Actually, the calibration is done here, so he will check these variations. And you have a loop. For each count 0, do HV, that's high voltage, at 1, so he set a number, and I didn't understand well this one. But if K is equal 1, then the droplet is moving. If else K equals 0, then the droplet is maintaining the place. I think this number they just get from the capacitance difference. That's how they know if the droplet's there or not. And for each count equals 1, do the top plate, GND, and ACT. I didn't find these subtitles for this. And if the sensing is bigger than the threshold, then the droplet exists. And if the tensing of smaller than the threshold, so there is no droplet. So it's a check that all the time is doing by the system just to just to check if the droplet is moving, if the droplet is maintaining, or if the droplet doesn't exist.
I have a question.
Yeah.
Is there you apply current or not?
Sorry?
In this device you apply current, right?
Yeah. You need to apply the current.
Current, yeah. And there is equal current?
Sorry?
There is equal current and
Equal current?
equal current
For all the electrodes?
yeah.
Oh yeah, all the electrodes receive the same
But
current.
when I see there, I think that they are maintaining the parallel series, isn't it? Can you
Where?
the
Previous?
Before slide? Before. Yeah, aren't they in the parallel series? But how can, if they are in the parallel series, then I think the current will be different.
No, it's different when the droplet exists. So the current will change. The capacitance difference is about this current. So when the droplet is in the electrode, the capacitance will be different. So the current will be different. That's why they identify that there exists a droplet.
That's why they arrange in parallel. Okay.
Yeah. Okay. No. So let's take a look at the circuit. The MC circuit is described as figure 5, where the count is the function selection of actuation sensing mode. So for the droplet location sensing, the top plate is switched to the ground level. The Yi-Tse glass go to the ground level. And the M3 and M4, that's M3 and 4, are turned on to discharge the parasitic electrical carriers from microelectrodes. In my understanding here, they just discharge these electrodes just to eliminate problems. So, like to go to 0, like a reboot. You just reboot the cell in the microelectrodes to don't maintain any energy there that will influence the result. So they need to clean and start again, clean and start again. Okay. So, and from the microelectrode. And after auto-zeroing, so this auto-zeroing, it means that we'll zeroing the microelectrode just because to eliminate the parasite electrical. And M1 and M2 will inject the micro A level charging current. So this will eliminate the parasitical electrical, and this will be the input of this microampere level charging.
So top plate and the electrodes is certain type of the detection modules. If the droplet is reached some depth areas, capacitance is changed.
Yeah.
So that variation is judged by this logic circuit.
Actually, this difference when the droplets is on the microelectrodes, the capacitance just changed automatically, and this will just discharge. For example, like an example here, you have the electrode, so the droplet is coming. So when the droplet's here in contact, the capacitance will be different.
Okay.
So they will detect, this microelectrode will detect the droplet. So when this droplet just passed to another electrode, this is now empty.
Okay.
So can be some remaining energy here, and it can influence the result. So they need to discharge. That's why they go to ground level, turn down to ground level to discharge this remaining current to get a new one. Okay. Just to not influence the results.
But how the water to move to another place?
Oh, good question. This water will move by electrostatic force. So, for example, if you have a flow of water and you just take a balloon and scratch in your hair, and you approximate, they will deviate the flow. So, because of electrostatic energy. So, it's the same concept here. By electrostatic, they will attract or separate the droplets. Oh, sorry. Okay.
So electrostatic energy is created by applying the voltage.
Yeah, you apply the high voltage, and this will create the electrostatic in the microelectrodes. Okay. So this is another schematic view. We have the microelectrodes here. So here is the droplets. They are activated. So the blue ones are activated and creating the electrostatic force. So it will attract the droplet here. So you can see that here, this red one is the silicon oil, and here only the droplet, the water, and here they are both together. So the 2D scanning image will detect you what is water and what is silicon oil. Remembering that why silicon oil is here is just to avoid the droplets to evaporate. Okay? So, as I say here, figure 7 describes the digital signals processing of droplet location map. And figure 7a, you can see the silicon oil that avoids the droplet evaporation. Okay? Go further, the digital signal processing of the 2D scanning image can be implemented with the sliding MCLK. This one I didn't find in the paper. What is exactly this? I tried to find on internet, but I didn't find. And I don't know what they want to say with this. Sorry.
It's okay.
And for applying different sensing thresholds. So based on the first qualitative sensing result, the area full of silicon oil will be decided. With the sliding sensing threshold, the next generated bits of sensing results imply that the location of the white water can be differentiated. So, as I say in the beginning, you need to face this as a pixel. So, when the droplets here and here is activated, well, about the capacitance difference, it will generate a bit that will be stored in the bitmap. That will be sent to the graphical interface. So you will have a graphical interface to check exactly where the droplet is and the oil tube. Okay. So we'll go to the mark here. The resolution, power consumption, and reliability will be considered for different bioreactions monitoring. So depends on the fluid that you were working. Probably they need to calibrate the system, because if they detect the capacitance difference, it can change from dye water to blood, for example. So probably they need to check this, and there is some adjustment to detect. And the proposed readout circuit employs the capacitance to time converter, that was a CTC, and time to digital converter. Thus, the two amplified sensing pulses named as sensing time and roller time will activate the digital controller oscillator and convert those two sensing pulse widths to digital codes. As I said, this digital codes is the bits that will be stored. And another term that I didn't find is that dot and route. I don't know what is this. I'm trying to find, but I didn't find an explanation about this. Do you know what is this, Professor? I don't know. Sure. Okay. So finally, user-friendly and real-time specimen reaction behavior is monitoring the graphical user interface. So it's not just not just stored and show the droplet in the graphical user interface. It's real-time. Every time you see the droplets moving and the oil and everything. I'm sorry, I didn't show the schematic. So this is the schematic that is very difficult to understand. But this is the high resolution capacitance, and this system is what is inside here. Okay, so block diagram of proposed CDC circuit for high capacitive sensing is just showing how it works and how it is assembled. Okay, so we have the implementation in comparison of this paper. The bioprocessor is fabricated in standard .535 micrometers CMOS, and the proposed process contains 900 MCs, as I said in the beginning. So let's see some characteristics. So this is the data acquired. The proposed architecture is based on the cell-based design concept to assemble the wall brick array. For biosignature detection, each MC is like an image pixel, as I said, and therefore the droplet position and genus can be drawn due to those MC sensing results. Here, it's not possible to see perfectly, but it has these lines are the microelectrodes, and they are changing. So it appears again MCCLK for scanning out the droplet location map. So these lines represent the location map. So that is being stored. All the data are being stored and sending to the graphical interface. So the location sensing results, as showed here, 56 and 57 here. So you have this gap here. So probably the droplet is not in the electrode. The times where the droplet is not in the electrode. And this is the bioprocessor here. And you have the probe. This probe is to put the micro droplet here. And as I said, the user can set the volume of this micro droplet to study. Okay, and this is the graph about noise in the system. And let me just grab this. So the noise floor measurement result, capacitance model. So in my vision is here, the droplet's here and the droplet is not, and here again. So the graph about this noise that I think they face as droplet is there or not. And again, the doubt and route. It's been this meaning. The just thing I found is that it's about the noise, but I didn't find exactly what is it. So you have the Yi-Tse chips that, let's take a look again. That's why we have the subtitle. Yi-Tse electro-wetting on dielectric. Okay. So you have these Yi-Tse chips, and here the researchers are comparing to the other chips in the market. So we have lab chip, sensor, nanobio, and this work. So, for example, actuation type. Yi-Tse plus pressure, Yi-Tse, and here just Yi-Tse. Position detector. The other ones don't have position detectors, but this one has position detectors by the microelectrodes and the microcells that is attached. So the droplet observer, microscope, and digital image. In this work, as I said many times, they use the graphical interface, and this is a big deal for them because the other ones doesn't have. You need to look in the microscope. So here it's easier to check the results by graphical interface. So in this table, he just compared many points with the other products as voltage and integration potential, the hierarchical design potential, and things like this. So this presents the analysis of the Yi-Tse chips. In this work, they provide an intelligent microfluid processor with field programming, system automation, automatic self-testing, this is very important, and calibration. So all the system just do everything. You just need to input the micro droplet and analyze the results. Okay. And this about the CDC circuit. The comparison of the proposed CDC circuit with other high-resolution sensing circuits. So it's comparing only the circuit. And I need to apologize because I don't have the background to understand this part. So I will study more about this. Because not my exactly field, but they're again comparing the points, good points and bad points, in relation to other products. So just to say exactly, the table shows the high resolution CDC circuit when both high occurs equivalent number of bit called NOP and energy efficiency. Figure of merit, that's FOM, are needed to consider for droplet monitoring or measurement window, especially the PVT. PVT is the process voltage temperature, so they need to check the temperature on the system too. And the PVT variation can be minimized by taking proportion. Okay, it's good to remember that this system uses very small current, so probably the temperature is not a big problem in this system. So compare it with the current solutions. The SS detector size will be reduced from 0.23 square centimeters to 0.05 square millimeters, with 460% of improvement in comparison to other bioprocessors. And the detection area is 0.025 square centimeters and 5 square micrometers. So all the system is very, very small, and all this is improved by 265% at least. For sampling enhancement from hertz scale, 2 megahertz, that's a big range. And the microscopic assays can be observed finally. With comparison of CDCs, the other ones, this work achieves better balance between energy efficiency and effective sensitivity, and also minimize the PVT variation, power consumption. So it's related, PVT, with the power consumption, because if you have a small power consumption, hence you have probably a variation in the PVT, because it's proportional to the current. Okay? So let's go finally to the experimental results. So this is the whole system and the environment, testing environment for the proposed bioprocessor. So what do you need? The computer that will have the image source, you have the oscilloscope, the power supply here, measurement readback that will send the bits to the bitmap that will show the image. You have the high voltage enable or disable to generate the electrostatic force, and the function arbitrary waveform generator. Okay, this is just to test the system. And here we have some results that, for example, high voltage circuit drives 14.5 volts voltage gap from droplet actuation. And an example shows the patterns versus the corresponding actions. So here you can see all the 900 microelectrodes, and this is the way that the droplets is sliding. And this graph, let me just it will not grow, but this graph is about the image generation, I think, and the droplet position detection. So it's the same pattern we saw here, and we saw in the previous slide. So here we have the picture of the plate, and here you have the graphical interface. So all the things that appear here will be represented here. You can check here the droplet. So this is the shape of the droplet, and he cannot just detect if the droplet is there, but it can detect the shape of the micro droplet. So you can see here the same shape reproduced here, because all the microelectrodes are sending the bit, sending the information to the computer to reproduce the shape. Okay, and see the illustration and description of the specimen status monitoring. So here is just the monitoring and showing the possibilities of the graphical interface that you can use. Okay, so in conclusion, this novel prototype solves lots of traditional development bottlenecks to implement the easy to control, because you don't need to make anything. You just input the droplet and the system will do all the process. It's easy to monitor because you have the graphical interface, and system automation and high accuracy sensing from biosafety detection purpose. So you have a high sensitivity in these microelectrodes, and combined with the system automation, which is very good because the system will do the self-testing every time, and it avoid errors. So the image that you see in the graphical interface will be quite similar to the reality in the bioprocessor. So with the digital processing and adjustable sensing threshold scheme, the 2D droplet location, genus, and reaction status can be differentiated and displayed in real time. This is very good. When you display in the real time, you don't need the microscope, you don't need anything to analyze. You just use the software. And here is just information about the size again, and how many microelectrodes they use, and things like this. Questions?
Okay. So now I understand the engine made a question and it is total. So it's your 4 guys have to make at least 1 question. Start one.
So,
Okay, start one.
so there are image processing and sensing. Sense processing is that the two processes are independent each other.
You need that. You're talking about CDC and CMOS?
Yes, I mean, if the drumlet is very small, then very small.
If you will detect it, this is
Yes.
better. Actually, in one part of the paper, he mentioned that there is a limit. So the microdroplet has a volume that you can use, but lower than this, smaller than this, maybe he cannot detect. So there is a kind of correct way to use the system. So you cannot just put the nanometer ball of water. It will not be detected. But they have a limit for how small this droplet can be be detected by the microelectrodes and send this information to the graphical user interface. And what the CMOS is just the processor that will store this information and send to the graphical interface. But as all you probably know, the CMOS is just a volatile memory. So it will be just disappear the information if you turn off the system. If you don't have a battery, this information will be lost. So it's in real time and changing the information and sending to the graphical user interface separately from the CDC. Because in my understanding, the CDC is just the circuit and the CMOS is the processor that uses the circuit as a part of this.
Thank you.
You're welcome.
Can you show university micro?
Sorry? What?
Figure one? Can you show figure one?
No?
Figure 1.
Huh?
Figure 1.
Figure 1? Oh, okay. Well, let's show figure 1. This one. Okay.
You said each scale have different
Let me just Can you repeat this?
current. Each scale can have different current.
Different current. Actually, in each electrode, actually all the electrodes will, in my understanding of this paper, will receive the same current. And this is the baseline to detect the droplet. So each electrode will receive the same current, and when the droplet is on the electrode, the capacitance will change. So they will detect the droplet is on this electrode. So every component receives the same current.
How they put droplets on the electrode?
Sorry?
How they put droplets on the electrode?
Ah, nice. There's an image here. Let me find. Here. You have a probe. So, yeah, probe is, for example, you have a pipe, you need to twisted pipe, you need to see inside, you just input a probe that will get there. So a probe is just a way to inject the liquid inside the system.
So just drop this on your drum and using this probe.
Yeah, it's like, let me show you. For example, you have some reservoir here, okay? And this is the system, for example. So this reservoir is filled of the liquid that you want.
How much quantity?
Huh?
How much quantity is
Oh,
it?
here in the
Yeah.
reservoir?
Yeah.
Oh, it depends on your wish, because you can have a gallon or it doesn't matter because you can just inject by syringe, you know. And for example, you can. This is not a real part of the system. It can be a bottle or it can be another recipient. Okay. So here you just connect the flow here, the liquid here, and it will flow by the probe, and you make the droplet. So if you have a big droplet and you want to separate, you have the matrix of microelectrodes here. So if you want to separate this droplet, you can just activate these electrodes and don't activate these ones. So one is, it will grab this part and the other ones will grab the other part. So they will be separated. So you can, of course, you can define the droplet volume by the system, but you can to separate the droplet as much as you can.
So chip itself is already silicon oil is fully introduced is under some chips. And then there are some two liquids, it's the silicon oils and
Yeah.
the other one.
Yeah.
So before introducing the drumlet, there are silicon oils already contained.
Yeah.
Right?
In my understanding, in this paper, the oil is already there.
Okay.
So you just put the liquid. But I thought if you want two different liquids, you can just use another kind of liquid. Questions?
So every electrode has different capacitance.
No, all the same capacitance.
If the drumlet is go a certain amount of areas, and that area have a certain different capacity
Yeah.
because of drum.
Yeah. This capacitance difference occurs when the droplet is on the electrode, and just to the meaning is just the purpose to detect that the droplet is there.
That is how the system detects the drumlet, where
Yes.
droplet is in.
Actually, we give the voltage there, so does not that the big drop, if there is a big droplet, it can be split into small droplets?
Yeah, you can separate. For example, you don't turn on the system, so you inject the droplet. Okay. So in the system, in the software they provide, you will set how many droplets you want. So, for example, you have this droplet with 1 milliliter, for example, and you want a half of this. So you will set in the software probably, and you will divide using the electrodes. So there is an image here that shows this. For example, where is this? I'll show you. Just a moment. Here. So here, there's can you see this green part? This green piece here, green.
Yeah.
It's one droplet, big droplet. So this is not divided yet, you know. So probably they inject a big droplet, and these blue ones are activated, and these blue ones are activated too. But inside there some electrode that is not activated.
No, if I want big droplet only. So I want to detect that. But by external force, can it be splitted or not? Without, I don't want to split it. But
You just want the big droplet.
droplet,
Yeah,
yeah.
because you can use, like here, you can see for one droplet, the green one, let's suppose that it's already cut here, but it's still big. You can see that this droplet covers many microelectrodes, so they are all working together to don't separate the droplet. If you want to separate, you just turn off these electrodes and it will separate. But if you want to keep the big one, they will use all the electrodes that is below the droplet. So it will not be separated.
So that systems can break the drumlet and accept the drumlet and
Yeah,
moving also
yeah,
as possible.
yeah.
These whole things can.
And in that, yeah, and that's why it's very interesting, because if you want to test some biological liquids or a drug or something else, you can just have the two materials. You can mix them, you can separate, you can mix again for how many times you want. You can just spin and separate again. So that's why it's very nice, this project.
Just one question. Is just any type of the experiment to using real viruses? It looks like some just talking about some systems.
Oh, they're using the main purpose of this systems is it have a laboratory on chip. So, for example, you go to a far place to, for example, a city that is contaminated. So you need to make some exams in the people. So you just collect the blood.
My question is like that. So this is the I understand the system. Is there any experiments to real experiments for detect or doing the some viruses?
Oh
Do you
yeah,
understand?
yeah. That's why this that I'm telling is that they need to collect some blood of the people and put inside this and mix with the reagent.
They use this of this.
Use this technology. And to make drugs, new drugs, and to make the blood tests and things like this. I want to show just more question. Okay.
I heard that in the middle of the layer is a hydrophobic, right?
Not in the middle. I will show you.
In the layer, that two
Here,
layers
there's a
is
hydrophobic.
The contact layer is a hydrophobic, right?
Yeah.
Yeah,
hydrophobic.
and the droplet is like they use DI water, right?
Yeah.
Yeah, and I think a lot of chemical liquid has a different hydrophilic or hydrophobic
Oh, correct.
mixture. And
Yeah.
is there any they mention about their limitation about hydrophobic or hydrophilic? Because
No,
I
they just mentioned the dye water, but I think they said this hydrophobic layer is Teflon. So probably if you have some liquid that is it will be grabbed by this layer, probably we will need to change this layer to a more hydrophobic layer. So they didn't mention this kind of questions, but I think they in this system they probably suggest a very hydrophobic layer to most of the liquids that you can test.
Because I think if they have different hydrophilic or hydrophobic property,
Yeah.
the contact area will be changed.
Yeah.
So I think they need to.
Yeah, maybe
So
for
that
dye water it works, but for blood it doesn't work.
Yeah.
Yeah, but they didn't mention it in this paper.
Okay.
Yeah, they didn't mention it.
One question, Virginia. Please, last question maybe.
They use the silicone oil
Yeah.
for prevention of the evaporation of the drumlet.
I'm sorry.
They use silicone oil for prevention
Oh yeah,
of evaporation.
yeah. They use the silicone to avoid the evaporation, and I think it's to contain the droplet, but I don't think it's necessary because the droplet can be contained only by the electrostatic force. So the main purpose of the silicone oil in this paper is to avoid evaporation of the droplet because they are using dye water and it can get some temperature, so it can evaporate with the temperature of the microelectrodes because of the PVT and because of the current. So,
Another reason why they use silicone oil is silicone oil is usually hydrophobic. So if you drop some water is not spread out inside of some some silicon oil. That is the reason why droplet is created inside the silicon oil. And another reason why they put some silicon Teflon. Teflon is just some hydrophobic.
Yeah.
So the droplet is hydrophobic and the Teflon is hydrophobic. So there are a little bit gap between the droplet and the silicon oil. That is the reason why droplet move easily in the system.
Yeah. Some I saw some other systems that use a fluor layer. That, fluor in the composition of this hydrophobic layer. So there's lots of different types of hydrophobic materials that you can use here. I will just show you some video. It's a very short video about another system working and a little bit explanation.
Hi, this is Oscar from Gaudi Labs. In this video I want to give you an update on the
It's
open
not about
Microfluidic
this paper, but
platform.
other one.
I especially want to talk about the new feedback feature.
Just 3 minutes.
The OpenDrop version 2 has 120 electrodes, is driven by Arduino Micro, has a OLED display, integrated high voltage supply, and now the working feedback amplifier. The setup that I use in this video is a foil ETFE 12 micrometer coated with a fluoropolymer that has spin cooled 20 seconds at about 4000 RPM, then cured 120 degrees. The ITO glass is also coated with the same material, and the gap for the liquid is about 0.2 millimeters, which gives a droplet volume of 1 to 2 microliters, and I just use water and ink. With this setup we get quite good and consistent results and a nice droplet movement. The video that you see now with the green droplet movement is open loop, which means that electrodes are just switched in a certain time pattern. The droplets are controlled with a joystick. It can happen if an electrode is not functioning well, like now, that the droplet gets stuck. That's why we need the feedback drive that I will demonstrate in this video. The OpenDrop version 2 has an amplifier circuit, actually by Wheeler Lab.
Here they have not a user interface on the computer,
with the new
but
library
they
can
have
read
this.
all 120
That's the
electrodes
droplet.
in less than 20 milliseconds, which means I get a
Here,
signal from each
what
electrode
your
if there
questions
is a droplet present on
The
it.
reservoir, you just
Now
connect
the droplets are
something,
doing
you
the
just
feedback,
pull.
which means the OpenDrop electronics can control the movement of each droplet, and as you see, when one droplet gets stuck, the other will wait until it finished to reach its position. The faster droplet waits for the slower droplets to reach its position. The feedback reading and the active electrode is also represented on the display. The driving of each droplet is also done by feedback, which means that only when the droplet reaches its position, the new electrode is activated. This means the drive of the electrode is asynchronous. As I turn up the voltage with the screwdriver, as you can see on the top left, the speed of the droplet is increasing. Also implemented is an auto routing. I set the goal, press the button, and the droplet will go to the position. The auto routing will also avoid other droplets or could even avoid defective electrodes, as you can see here. With the joystick, I set a new goal, hit go, and the droplet will go there.
I want to show just one more very quick video that is they're using in Toronto University. It's 1 minute video, very quick. Real.
In our modern world, technology keeps getting smaller and faster. What once took whole buildings and entire rooms now fits on your desk and in your pocket. What if you can shrink down an entire lab to something the size of a credit card? Here in the Wheeler Lab at the University of Toronto, we focus on miniaturizing chemistry and biology, effectively creating a lab on a chip. At the core is a technology
It's very
called
nice.
digital
It needs a lot of
microfluidic, which allows us to move tiny droplets
Test
of
drugs
liquids
and
using electrostatic forces.
the
We can
electrostatic
combine, mix, and split these small droplets and probe them with high-tech sensors to get information faster. This technology could allow laboratory tests to be performed at the point of need, where tiny droplets of sample can yield a result in seconds. With funding from NSER, we are making this technology cheaper and simpler to help Canadians and the rest of the world.
So this is a real example. So that's it, my presentation. Thank you so much. Have a good night.
Very impressive presentations. Thank you.
Thank you.